Carol, can you hear us? We can't hear you.
It seems you're muted, Carol.
Operator error, sorry about that.
It
Usually is. Usually is.
Hey, Carol, good to see you.
Good to see you. So I'm running a little late. I'm going to have to reinstall Zoom on my original computer. I had to reinstall everything else. I left most of my programs. So anyway,
no.
such are the joys.
Yeah. Did you get everything back?
No, I've got several programs I've got to reinstall manually, but
Oh, wow.
it got corrupted. The Microsoft portion of it did.
Oh my gosh. It's awful when your computer crashes or something like that happens.
And I know I probably had probably half of my programs I don't use very often, but in case I ever needed to, I sort of like
Right. Yeah, definitely. You kind of get used to what's on your computers and, you want to depend on it. So
That's exactly right. Hi, John. I don't think I've met you before.
Hey, no, I can't say that you're familiar either. So, Hi, nice to meet you.
So nice to be here. Yeah, you bet you.
you look like you've got sunshine there, Carol.
Well, yeah, a little bit.
That's good.
Is it cloudy in your direction?
Yeah, usually when I get your weather like the next day, so I'm glad to see sunshine. It's definitely cloudy here.
I think it's Sundays when we're supposed to get rain on Easter Sunday.
Oh, great.
So maybe you'll dodge the bullet.
Yeah, I think I'll get by.
I've known it to snow a few times on Easter Sunday, so it can be all over the place.
You can keep that to yourself. I've had enough this year.
And that's true. Some place in the north, it seems like it was Montana in the last couple of days, they got 7 feet of snow.
Oh my gosh. I just came back from Alaska. They had 93 inches this season in snow.
Wow.
Yeah, I've never seen snow so deep. It was really deep.
It sounds like you had some wonderful observing when you were up there.
Oh man, it was unbelievably beautiful. Yeah. Yeah, that's what's inspired me to start on a Aurora series.
Finally, another sunspot on the sun today.
Yay.
Yeah, they were making progress.
Yeah.
Yeah. It's hard to believe how active the sun's been.
Yeah, it's been beautiful.
Yes, it has been.
It took a little bit of a break and now it's back again.
That's what we like to see.
Our little
Well, hello everyone. This is Scott Roberts from Explore Scientific and the Explore Alliance, and we welcome you to the 16th Astronomical Live program hosted by Terry Mann. Terry, why don't we get started? It's a pleasure to have you on as always.
Thank you, Scott, and thank you for broadcasting this. We appreciate it.
Thank you. Thank you. It's a real pleasure.
So what I would like to do is just go ahead and start with David Levy and ask him if he would open us up here and get us going.
Well, thank you very much, Terry. It's a real honor and pleasure to be here. I love going to the Astronomical League online events, and I would have loved to come to Albuquerque this summer, but it turns out that I won't be able to come. But I am here today, and I love these online meetings. Our quotation for today is going to come from sort of, with an emphasis on sort of, from Shakespeare's play Julius Caesar. And you know how he wrote at the very end when Brutus gets killed and Mark Antony is standing over Brutus's body and gives us, "This is the noblest Roman of them all" speech. Beautiful, beautiful speech. But I like to think that after he's done writing that speech, finishes the play, and he goes and sets up his telescope down fairly low. He probably takes a night flight to Tucson and sets up an Explore Scientific telescope, and he looks at Omega Centauri. If any of you have seen Omega Centauri, this is a cluster to beat all clusters. It is, I think, the most beautiful star cluster in the sky, one of the most beautiful things in the sky. And I would like to think that after Shakespeare looked at it with his telescope, he would have written these lines: "This is the noblest star cluster of them all. All the star clusters, save only he, did what they did in envy of this great cluster. He only in a general, honest thought and common good to all made one of them. His life was gentle, and the elements so mixed in him that nature might stand up and say to all the world, 'This is a star cluster.'" Thank you very much, and back to you.
Thank you, David. That's good. I like that.
Beautiful.
All right. Tonight, we're going to do something just a little bit different. I am going to do a presentation. So I am going to work on sharing my screen. And I'll explain to you why I thought it might be important at this time to do this. And some of you know I just returned from Alaska. I was there for a little while, and this has been one of the most beautiful trips I think I've ever made to Alaska. As you know, these are 3 of my images from, I just came back about 10 days ago. These are 3 of my images from when I was back there. So why I am doing this is I am very, very impressed. The colors, oh my gosh. You know, I have been there before, seen a lot of greens, mostly greens, some reds, you know, some really gorgeous reds. But I was amazed at the amount of color that I saw on this trip. Every night was colorful. It didn't matter what time it was, whether it was sunrise, sunset, in between. The skies were beautiful. And I am guessing this has to do with the activity on the sun, with solar max being on the way. And they are predicting we'll hit solar max about 2024, 2025. So what I want to do is start a series of Aurora, because I think I've been amazed at when I've flown or been in places and people ask about, you know, where'd you just get back from, or have you been traveling, or what did you see? How many people have Aurora on their bucket list? So I felt like it was important. We've got 3 probably really good years here that we are probably going to see some of the best auroras we have seen in a while. And so for people on the bucket list that maybe don't know a whole lot, or maybe have some questions, I thought I would start up a series about this and take you all the way through from planning clear to getting images and wherever else we go at that point. So what I'm going to do here is just touch a little bit on what I will do, and then we'll talk a little bit more about how it's going to be presented at the end. But a lot of people want to know, where can I see the aurora? Well, I have seen the picture here in the middle. I did see up in the UP of Minnesota. They have many lakes up there. I don't know which one this was for sure, but this was up off the Gunflint Trail in Minnesota, way up towards the UP. And the UP of Michigan, oh my gosh, and Marquette, up in that area. That is another great place in the lower 48 to see it. I've seen it in a lot of in a few of the northern states. Wisconsin's another good one. And every once in a while, when we have a very large CME, I have seen it in my backyard, my front yard, and that is what this picture is to the right. That is actually in my front yard, shooting out of my front yard. And you can see the reds, the colors. It's amazing. So depending on how large of a CME, a coronal mass ejection from the sun we have, it could be possible to see aurora. I've heard of it as far south as Florida. I have not seen it down there, but I've seen pictures. So there is a time and a place, if conditions are right, probably anywhere in the US, you might have a chance of seeing the aurora. But what about outside of the lower 48? Now, I wouldn't mind going to Norway, but from what I've read, cloud cover can be a serious problem there. And these other places, Iceland, Canada, we've seen beautiful pictures from Canada. Alan Dyer's pictures are just outstanding that he has shot from Canada. I have some friends that have been to Iceland that theirs were just beautiful. But I chose Alaska. I tend to go to Alaska. And part of the reason I chose to go to Alaska is just like conditions like this. Now, this is actually live. I need to kill the sound. You're going to hear me walking all over the place. This is live real time. And
Wow.
yeah, this is up by the Big Dipper. This is what you saw naked eye. This is not what I've ever seen in Ohio. You know, when you get way, way up north, this is a type of thing that you will see. And that is why, one of the reasons why I choose to go to Alaska. The others are, Alaska's easy to get to. I mean, no airfare is cheap, don't get me wrong, but major airlines do fly there. And I always, whenever I'm planning a trip to do any kind of imaging or anything, I always want to know what else have they got that I can do. If I get clouded out, and believe me, on one of my trips to Alaska, I was just about totally skunked. I had clouds almost my whole trip one time. So you need to look and see if there's other things that you can do, and you know what would be there that you could do. But a Fairbanks is really ideal because you are under the auroral oval, and that is the ring-shaped zone over the far north where the activity is actually pretty well concentrated, and that's why you see it so active. And this time I was in Alaska for quite a few days, and I only had 2 cloudy nights. And what was amazing was the weather forecast predicted clouds almost every night. And it did. It had a few clouds, but then it cleared off, and the nights were totally amazing. And as I said, there's plenty of things to do in that area. I don't spend very much time in Anchorage, but maybe as the CMEs get stronger, I'll be more comfortable, because for me, I'm there to image the aurora, and I want to be as far north as I can get to do this, because if it's a small CME or kind of weak, it's not really going to go clear down to Anchorage. So I spend most of my time around the Fairbanks general area. I travel around a bit through there. And so they want to know, well, when's the best time to see it? Well, usually when I go, very honestly, I'm there new moon in March, usually. This time I stayed the latest in April I ever have. And as you see there, April, usually I stayed till the 4th one time, and I think I stayed until the 6th this time. And you're losing daylight. You're losing darkness, and you're losing it pretty fast. As you can see here, the course of April in Fairbanks, you rapidly have more daylight. The length of the day in April from the start of the month increases by 3 hours and 19 minutes. So an average of every day, you gain almost 7 minutes of daylight every day in April. So I don't really stay late in April. It is something to see in the beginning of April. This was taken at sunset, and you can see at sunset, you have the purples and you have some of the blue. Sunrise and sunset is just a beautiful time to shoot the aurora if it is out. And, you know, it is gorgeous, but I just don't stay late in April. I try to spend most of my time in March and maybe the very beginning of April for that reason. And again, in the lower 48, when you can see this, anytime the conditions are right. I mean, I've seen it in Ohio. I haven't seen it here since 2003, maybe. But if it's dark and conditions are right, you can see it anytime that it is dark. And believe me, it's nice to watch the aurora when it's warm. I have been able to do that a few times. In Alaska, I'm dressed up. You know, you are totally dressed up in March. I think our lowest temperature that I saw this time was somewhere, I'm thinking where I was at, it was around 22 below. But most of the time it ranged somewhere around 10 below to 15 below maybe in the evenings. And there were times it was just hovering around zero. Really just depends. Now, as I said, you can see the aurora anywhere. Okay, I am on Lake Superior chasing aurora. And this is the kind of stuff can happen. This is what can happen. Lake Superior came to life and pretty much totally nothing there to see. But again, I'm up in the UP of Minnesota, and this is Lake Superior. And even though it was nasty out, it still had a beauty of its own with raging nature. It was something to see and just to stand out in the snow and watch that. So always consider wherever you go, weather is going to play a factor, and have a backup plan of something to do if you don't enjoy the weather too much. And what else we will cover, we'll get into equipment that you'll want to have, fast lenses, fast glass. Maybe you've got a newer camera that can handle the higher ISOs that you don't need quite as fast of a lens, but it's always nice to have. But by no means do you need to have a brand new, expensive camera and expensive lens to do that. You can see a lot of phone pictures of the aurora that you can at least take home, you know, a piece of the aurora or a part of the aurora. So depending on your equipment, honestly, you will be able to get something. But the first thing too you have to consider, and I have to work on this whenever I fly, getting that equipment wherever you're going to go. I do not check my lenses or my cameras or my laptop, so I am always carrying a very heavy carry-on. That is something that you always need to consider about everything that you are taking with you. How you're going to do it if you fly, that becomes an issue. And clothing. In Alaska, you definitely, in the wintertime, you definitely need to make sure you have the correct clothing or you will be very cold. And honestly, over the years, I bought almost every piece of clothing as far as outdoor while I was in Alaska. They just, the time you go up there in March and it seems like your prices are a little bit cheaper. But they have clothes that are made for their weather, so it makes it nice. Weather is always going to be a consideration. It is to me whenever I'm going anywhere. If I can make a last minute guess, then it's a lot better. But most of the time, I'm checking historical data, and that doesn't always tell you everything, but it gives you a good idea. And think about how long you need to see. I know they say in Alaska, if you stay 3 or 4 days, you have a very good chance of seeing aurora. And I do believe that. As long as it's clear, you will. You won't see, you might not see the active stuff that I just showed you of the one video, but you will see green aurora within, I would guess, 3 to 4 days if it is clear. And again, figure out what else you can do. There are other things there. There's a lot, and a lot of them are your tourist trap type deals, but it's still, if I'm someplace, I don't mind looking around at someplace new. if I'm someplace different. So we'll cover a lot of that. And this was a nightmare when I went to the total eclipse in Aruba in '98. You can see all the equipment we're carrying.
Oh, yeah.
And we carried a ton of equipment and we flew, but it's something just you have to think about getting it moved around and lifting it, getting it sometimes through customs. I've never had a problem with customs flying equipment, but I've always done everything to make it as easy as possible. But you can overload. The problem is, I think with a lot of us imagers, or at least maybe me, I think I need to have lenses to cover anything that I might see. If I don't have the lens to cover what it is I want to shoot, I'm really not real happy. So I take what I need with me and try to figure out how to adjust that weight limit. And again, some of what we're going to cover is understanding the aurora, the weather, choosing a location. And a lot of times that location might be here in the US. It might be outside of the US, could be Alaska or Canada, or, think about the location you're going to and what you're going to deal with. Equipment, what you will need. We're going to cover imaging the aurora and time lapse and video for aurora, and clothing, and preparing for possible emergencies. That is something, traveling in Alaska, there's times you're out running around all night long and it can be 22 below, and you have to think about things like this. Whether your phone will work in the area you are at, if you need another way to contact people. There are a lot of possibilities. And when you're traveling in an area where weather is can be a real problem, you really have to think about things like this that maybe you wouldn't. I mean, the first couple of years there, I didn't. Like I said, the more snow I've seen in Alaska and the more bad roads when I've been there, I've really thought a lot about that. And we'll cover whatever else comes up with that. So right now, I just haven't got every detail worked out. So we will be announcing this series as soon as we decide the best way to present it, because I want to do it in a way that just makes it simple and easy for people to interact. It will be announced on the League Webb League's Facebook page. I'm going to twist Scott's arm and put me on the Global Star Party Summit.
They'll take a lot of twisting.
We'll definitely announce it there or on AL Live, but I'm not quite sure the best way to present it. And so I want some input on that. So we will definitely let you know. So that is going to be the end of mine. And
Great.
Carol, as I'm shutting down, I am going to go to you.
Thank you, Terry. You've whetted our appetite to go to Alaska and look at Aurora and spend some time and take it seriously. It's been on my bucket list for a while. I've seen one or two, but I need some more.
Yeah, everybody that I've talked to, I've heard that comment more times in ever since I've been home and traveling home, and that's another reason I thought this is a time to do it, because so many people have questions and really would like to do this. And it, depending on where you go, it can be an expensive trip. So you need to have all the knowledge that you can. So, but I think that's why it's important. So David, I guess you wanted to say something too.
Yes, I do. I wanted to congratulate you, Terry, on this wonderful presentation. If this is the quality of presentations we can expect from the Astronomical League, God bless you. This is wonderful. My first Northern Lights display, I'll never forget. It was before I knew how to take a picture. It was on the 4th of July, 1966, at the Adirondack Science Camp, the same site where we do our annual retreat now. And it was magnificent. It started at sunset and the sun was going down and had gone down and the twilight was in the west. But instead of revealing a beautiful sky, the twilight appeared to just shift over to the north. And that was a bright glow that turned into a ray arc. And finally, it ended the night with an all-sky aurora with coronal effects, and wonderful. I'll never forget it. And it was one of the most thrilling nights I've ever had in my life. Terry, thank you so much for your talk.
Well, thank you for your comments, David, because I think that's the way so many people feel, especially when you see a really active display. It just knocks your socks off. It really does. It's amazing. So thank you. I appreciate that. Okay. All right, Carol, let's
All right.
see.
As far as the league, we've got a little bit of information. As most of you know, we didn't have an active in-person Alcon for 2 years, but now we're in the middle of registration and things are going very well. One thing for all of you master observers who are listening out there from the league, one thing, those have piled up a little bit, the number of people who have gained those awards, but who haven't received the plaques yet. So we're going to publicize this as much as possible to get as many people to Alcon to get your award in person, the plaque, as possible. We would like to have your information, however, by the end of this month or the early May at the latest, so we can make sure we have the plaques ready and so on. Anything you want to know involving Alcon 2022 can be found at alcon2022.astroleague.org. Whether you have not made your room reservations yet at the Embassy Suites, and by the way, that is a very nice hotel. Each room is a two-room suite, so it's very nice, very reasonable rates. And so make sure you go to that link. It will give you the registration information as well as the link to actually go ahead and reserve your room. So there's a lot going on there. And if you, like I say, if you've been thinking about, well, I've got my observing awards together, just go ahead and do it. Get registered, and we'll see you in Albuquerque. We're going to have a lot of guest speakers there, as always, at our Alcons. And one of the things that some of you may not have seen is one of the large array facilities there in just out of Albuquerque, about an hour's drive out. And that's going to be held at the end of Alcon on the Sunday. And it will allow you plenty of time to thoroughly enjoy the experience. So I would encourage you to stay over a day or two. We've got some special rates, room rates, not only but during the convention, but a couple of days before, as well as a couple of days after. So I'd encourage you to do that. Again, this year, we've got a lot of entrants from the youth award winners, as well as the adult winners. So it's going to be a great experience. So hope to see you all there. And I think that's it for right now. Terry, back to you.
Okay. Thank you, Carol. Yeah, I'm looking forward to that. Do they still have that? Is it Harrison Smith that they're going to do?
Yes, I neglected to mention that the astronaut, there's going to be a special event with him, and that's separate from the rest of the convention, a dinner with him. And it's on the registration form. You could pre-register for that at a very reasonable price. And he is very articulate, and he is always willing to share his experiences in outer space. Wouldn't it be great to have that phenomenon, that experience?
Definitely.
Yep. But he's more than willing. He's really very accessible to the public and the members. So that's.
I'm looking forward to that. So, okay, Carol, appreciate it. So now we're going back to me again. As you know, we ask questions for at the Astronomical League Live. And so what I'm going to do is get this ready again. This time, as you can see, this will probably be the last time we do 2022 calendars. There'll be 3 calendars given away. And if we're shipping internationally, please remember we have had problems with it. It has slowed down shipment. So this will be the door prize for tonight. And please answer the questions in the next 30 minutes. This one's not like the GSP. I will be announcing the winners after John gets done speaking, and someone from the Astronomical League will contact the winners sometime in the next week or so. So here are the questions for tonight. How wide is the cosmic bubble that surrounds Earth? I'm going to do it again. How wide is the cosmic bubble that surrounds Earth? Next question. How many seconds has the Hubble Space Telescope been operating since January 1st, 2022? That's a tough one. How many seconds has the Hubble Space Telescope been operating since January 1st, 2022? And the last question, what astronomer coined the name Aurora Borealis? Please send your answers to secretary@astroleague.org as soon as possible. And we're not going to give the answers. I'll stop right there. Yeah, that's why I have to put that in there. I have done this before. So what we're going to do now, we're running really quick on time, but Scott, let's just take maybe a 5-minute break. Let John get set up and we'll just
Okay.
take a 5-minute break and we'll come right back with John Wenskovitch.
Sounds good. Okay.
Okay,
So here we
thank
go.
you.
Let's do this and I will adjust the time.
Yeah, as long as it's around 5, that's good.
Is 10 minutes around 5? Maybe not.
Hey, if we need to do 10, we can do 10.
We don't need to do 10. Here we go.
Oh, you're good. Okay, thank you, Scott.
Well, that was a silent visualization of J West at the L2 point. And I'm going to turn this back over to you, Terry. But thanks for tuning in to the 16th Astronomical League live program, you guys. Here we
Thank
go.
you, Scott. Now, I have a question of that visualization. It was
Sure.
pink underneath. Does that actually happen? Could it be a reflection of sunlight? Or maybe John would know the answer to that. Or it
don't
might
know.
just be how visually nice it looked.
John does data visualization, so maybe he has a good answer.
No, and unfortunately, I can't say that I have a good answer for that one. It might be a bit of artistic license. It might be some other effect that they've modeled.
Yeah. Okay. I just wondered because it turned to such a pretty shade of pink underneath, and I thought maybe it's sunlight or something. So, all right, we will get started. Our keynote speaker tonight is John Wenskovitch. John is a visual analytics researcher at Pacific Northwest National Lab and a professor in computer science in the computer science department at Virginia Tech. His current research focuses on human AL, co-learning and teaming, trust in machine assistance, human in-the-loop data science, analytical provenance, and the application of visualization to both the sciences and cybersecurity. He teaches courses on information visualization, data analytics, computer graphics, and human-computer interaction, which I think all sounds amazing. Your job must be really amazing. So, John, I would like you to just go ahead and take it away.
Sounds great. Thanks so much for the introduction. Thanks for having me as a speaker here on AL Live.
Well, thank you for being here.
Let me give the usual commentary while I share my screen and get all my windows organized. So hopefully everybody is able to see the presentation. Yep. And we're ready to get started. Okay. Great. So before I really get started, I want to definitely make sure to thank John Goss, who connected me to be able to give this talk for a second time. So the history of this talk is that I was originally asked to present on the James Webb Space Telescope and the Lagrange points during a meeting in February for our Roanoke Valley Astronomical Society meeting. And now you all get to see, I guess, an extended version. You get the director's cut, where we get to talk a little bit more about James Webb, and we get to talk a little bit more about the Lagrange points. But I want to get started with this presentation by talking about something that's not in the title of the presentation, and that's the Hubble Space Telescope. So Hubble, well, it's iconic. We all know Hubble. We all know the Hubble Space Telescope. I would make an argument from a scientific perspective that, you know, it's probably the most important thing that NASA's ever done, even beyond that whole landing humans on the moon thing. The Hubble Space Telescope, I mean, it's been doing science for decades. It launched when I was 2.5 years old, and I've had my PhD for more than 2.5 years, and the whole educational span in between, the Hubble Telescope has been doing great science. And just to pull up a couple of images to really give Hubble its due, right, we've got the pillars of creation in the Eagle Nebula in Messier 16, and we've got some of the impacts of the Shoemaker-Levy 9 comet on Jupiter that were taken by Hubble. The Hubble Extreme Deep Field, looking way off into the past, looking way off into a tiny little sliver of space and seeing all of these galaxies that are just so distant and so tiny. And even being able to view exoplanets, being able to directly image planets outside of our solar system. The Hubble Space Telescope, I mean, I can't even say enough praise about how much work it's done. But it's also 32 years old at this point, and that's just 32 years in orbit. It's time for us to start planning its successor. And even though James Webb isn't, you know, purely a successor to Hubble, that's the way it's been billed. And so I'm going to go with the NASA lingo of James Webb being the Hubble successor. So one of the nice things about Hubble is that it's not too far away. In fact, here's a nice visualization of the Hubble Space Telescope orbit. It's close to Earth. It's a little bit higher up than the International Space Station, and it's a little bit smaller than the International Space Station, so it's a good deal dimmer in the sky. But you know, whenever the sun angle is right and whenever it's in the sky close to sunrise or sunset, you can go outside and you can see the Hubble Space Telescope kind of just drift across the sky. And another benefit of Hubble being so close is that we have the ability to go off and fix it. If you'll recall from the early 90s, when Hubble was first launched, it was a little bit of a disaster because of some issues with the main primary mirror. And so the very first servicing mission 1 that you see here, had to install some corrective optics on the Hubble Space Telescope, so that instead of having images that were a little bit messy and blurry like this one, that's Melnick 34 star, which has this kind of distortion as a result of this aberration in the primary mirror. You know, we were able to correct for this, and we were able to get our amazing images that we're so used to seeing coming back from Hubble. Okay, so Hubble, it's nearby. James Webb is not. And one of the reasons why the James Webb Space Telescope is not going to be positioned anywhere close to Earth is the fact that Earth is warm. Maybe not quite this warm. This is an image that I see on a lot of blog posts whenever they're commenting on climate change. But Earth is a warm place. Earth takes in light from the sun, solar radiation. It warms up. And it generates infrared emissions. It reflects heat back off of its surface. That is a bit of a problem for the James Webb Space Telescope, because the James Webb Space Telescope is designed to be an infrared observatory. It's designed to look at these longer wavelengths of light. And well, if we're going to have an infrared telescope, we need to make sure that our infrared telescope stays nice and cool, stays away from the Earth, and doesn't get all of this bright heat reflecting away from the Earth and messing up all of its images. And so whenever they were designing the James Webb Space Telescope and figuring out what the mission parameters were going to be, they decided to put it somewhere else. And the place that they decided to put it is, well, it's called L2. And that's the main topic behind this presentation, the James Webb Space Telescope and what exactly is L2 and the overall Lagrange Point family. So here is a nice infographic that NASA released as far as the James Webb Space Telescope launch and deployment goes. So it launched from Earth on Christmas of last year. It took off and it started assembling itself. It started unfolding, the mirrors locked into place, the sun shield locked into place. And eventually, after all of these individual steps, after about 30 days had gone by, it made it out to this point here in space called L2, which that's great, but it doesn't really communicate all that well about where L2 is. If I can give you a little bit of context, this gray oval that you can see all the way back here, that is the orbit of the moon. So L2, we can see just right from the very beginning here, is well beyond the orbit of the moon. We're going way, way out into space. There are definitely reasons why we'd want to take it that far out away from Earth, but it also seems like that's going to be something that complicates our mission, right? We first off don't have the ability to do quick and easy servicing. It's going to be really distant, and so we don't really have the human spaceflight capability to be able to go out there at the moment, and we've never had the ability to get that far away from Earth. In addition to that, well, if we're getting this far away from Earth, aren't we going to eventually lose the telescope? Isn't it eventually going to drift away from the Earth even further? What's so special about this L2 point that we decided that we want to put it there? Let me give you just another quick example about just how far away this L2 is. Here's a nice NASA image where everything is not to scale, as you're going to see from a lot of this presentation. There's a good bit here that's not going to be to scale, but you can see that up here we've got Hubble. Hubble is in orbit around the Earth, and they've got this number 570 kilometers. For us in America, you know, think of it as 400-ish miles. We've got 384,000 kilometers to the moon. We've got 1.5 million kilometers to L2. Just how big of a distance is that? So let's take the size of the Earth, the entire big planet, and let's reduce that down to be about the size of a quarter, which is a little bit less than an inch across. At this scale, Hubble is this far away from the edge of our quarter, 0.0427 inches, which is not an easy number to try to parse. So let's switch back to metric for that one. It's a millimeter. The Hubble Space Telescope is a millimeter away from the edge of this Earth coin as it orbits around the planet. Okay, so then we've got the moon. The moon is 384,400 kilometers away. It's going to be a little bit more distant. At this scale, the moon is 2.4 feet away. That's a pretty sizable distance. That's a big step from low Earth orbit whenever we're a millimeter away from our quarter to being 2 feet away from our quarter. But then we've got this 1.5 million kilometers for L2, and that is going to be further and further away still. On this scale, whenever Earth is the size of a quarter, we're putting this $10 billion observatory about 9.5 feet away, 9 1/3 feet away. It's a good long distance away. And this second image, also generated by NASA, which better labels the orbit of the moon, really kind of puts that out there, right? We've got this huge distance from the Earth to the sun. We've got this huge distance from Earth to L2, and this, for some reason, is where we're going to put this $10 billion telescope. So that brings us to the other major point of this presentation, and that's talking through, well, what is a Lagrange point? What are we actually talking about whenever we're talking about these Lagrange points, of which L2 is one of the 5? So before we get too far into this, let me just do a quick note on terminology. So I'm going to try to be pretty consistent with using Lagrange point or Lagrange point. I can pronounce it either way inconsistently. But sometimes you'll hear Lagrangian point. Sometimes you'll hear L point. Sometimes you'll hear libration points. These are all equivalent terms. These are all referring to the same thing in our universe. These are all L points. These are all our Lagrange points. So with that terminology note out of the way, what is a Lagrange point? What is L2? Let's start off with this image that, again, I pulled down from Wikipedia. These are our Lagrange points, and we label them as L1 all the way up through L5. And you can see that they're just kind of almost oddly distributed around this image. We've got Earth sitting here with the moon in orbit. And we've already seen that L2 is somewhere out in this direction, away from the sun side of the Earth, well beyond the moon's orbit, somewhere out here. But we've also got L1, and it's also on the outside of the moon's orbit, and it's on the side closest to the sun, which is interesting. So we're saying that we've got this point here, L1, which is, well, interesting, but why is it interesting? Why is L1, L2, L3 all the way over here, L4, L5 kind of off on the sides? Why are these so important? So it turns out that these are places in the universe where spacecraft can be safely positioned because of a balance in the forces acting on these spacecraft. And so let's take this image and let's make it just a little bit more complicated. So if you're used to looking at topographic maps, you can imagine this as a topographic map. If you're not so used to topographic maps, well, you can kind of think of this as trying to show the gravity wells of the sun and the Earth. If you want to think about it in 3D terms, here's a very blurry screenshot that I took of an animation from NASA, where you can see these gravity wells dipping down for the sun and for the Earth into these cones that drop down below the spheres. So going back to our 2D view, L1, well, it looks like it's kind of almost on this little saddle point, right? We've got the gravity well of the sun dropping off to the left. We've got the gravity well of the Earth dropping off to the right. And L1 is kind of balanced. It's a really nice position where those forces end up being nicely balanced. That one is probably the one that intuitively makes the most sense. It's in between these two different major gravitational sources, and it's at this nice balance point. But it turns out that if you start looking at all of the interactions for how these gravity wells bend and curve space, we've got some other points that work out to balance these forces really nicely. And L2 is one of those points. It's also sort of on a saddle. It's at a point where the gravity well of the Earth is coming up away from the Earth, or if you want to think about it from the top downward, dropping down to the left. And as we're getting further and further away from the sun's overall gravitational field is getting a little bit weaker, and so it's slowly dropping off toward the right. And so this is another one of those nicely balancing points inside of this Earth-Sun system. We've got L3 over here, and L3, well, it doesn't quite look like it's on so narrow of a saddle point, but you can see that there's a curve coming up around the side, and you can see there's a curve coming down around here. It is still on a saddle point. It's just a much, much broader saddle overall in this gravitational space. And then we've got L4 and we've got L5. And these are, again, not really at saddle points. I guess really they're not at saddle points at all. You can almost think of them as being at the top of some really smooth hills. And so L4 and L5 are a little bit more regional. They're not really mathematical points, although there is a mathematically optimal location. But it is more of a range of places where we could try to put spacecraft in a nice gravitationally balanced way. So again, we've got all of these different renderings that are trying to communicate where these different Lagrange points are. Here's just one more that I wanted to add in because maybe it's a little bit easier to stare at. It's not as quite a bright and colorful image, but you can still see some contours that are drawn here, and you can see that L1 is kind of at this nice intersection, L2 is at this intersection, L3 is at this intersection, and then L4 and L5, well, they're kind of over here at the tops of these hills. Okay, so those are our Lagrange points. Talk over. Well, not quite so much because there's a lot more to really talk about with respect to Lagrange points. And the first thing to talk about is maybe a little bit of the history. So how did we figure out that these things exist? And it turns out that this is not a space age discovery. These are points that were identified as being at least mathematical curiosities all the way back in the 18th century. And so here is a copy of a mathematical paper. You can tell that it's an 18th century paper because they were writing papers in Latin at this point. And this is the first time where it was published that there are some of these nice balance points that exist out in space. Just taking a quick pass at trying to translate the title, it comes out to about the rectilinear motion of three bodies attracting one another. And so we can break that down a little bit. So three bodies, we're talking about three different things. We've got two big, massive gravity wells. We've got the sun and the Earth. And then we've got this third body. And this third body is what we'd like to place at that nice, balanced gravitational point. And then there's the whole thing about attracting one another. Well, that's the gravity piece. We've got the spacecraft pulling very, very slightly on the sun, pulling very, very slightly on Earth. But then the other way around, the sun is tugging on this spacecraft, the Earth is tugging on this spacecraft. And then there's the motion piece, because we also have everything in orbit around the sun. And so we need to think about, well, we've got a messy coordinate system that's going to be constantly changing because of this orbital motion of the Earth and how that's going to have an impact on these Lagrange points. Speaking of Lagrange, if you look a little bit further down at the author of this paper, the author of this paper is not a guy named Lagrange, which was something that I didn't know about when I started to prepare this talk. I would, under the assumption that, hey, all of these points are named after Lagrange, so he must have been the guy who discovered them. But it turns out that the first three, L1, L2, and L3, were discovered by everyone's favorite 18th century mathematician, Leonard Euler. And so my, kind of conspiracy theory mind is thinking along the lines of Euler already has 6,000 different things named after him. He's one of the greatest mathematicians of all time. And so even though he found these first 3 Lagrange points, they just kind of threw the whole thing over to Lagrange whenever he found numbers 4 and 5. Maybe that's what happened. Maybe it's not what happened. But that's at least my headcanon for why these discoveries from Euler ended up being named after Lagrange. So it turns out that these two folks did know each other, and they were in pretty regular communication. And so let me just give you a little bit of an extended bit of the history lesson here. So Euler was born in 1707. He was a Swiss mathematician. But back in the 1700s, there were a few different really prestigious places where mathematicians would go and work. And one of them is the Imperial Russian Academy of Sciences in St. Petersburg in Russia. And I just want to take another quick tangent to note that all of these different places are named Academy of Sciences. And I really wish that universities still were called something like Academy of Sciences, because it just feels a bit more prestigious. But anyway, that's a digression. So Euler goes off to Russia. He goes to St. Petersburg. He works at the Russian Academy of Sciences for a few years. And then, well, there's a little bit of political instability that starts to happen in Russia. Peter the Great passes. There's some issues with succession. There's some issues with the economy. And eventually he decides to make a move to Berlin, to the Royal Prussian Academy of Sciences, where he spends the next 25 years. So there's a couple of different dates that I found for when Euler actually proved the existence of L1, L2, and L3. I've read that it's somewhere around 1750. I've read 1765. What we do know for sure is that he published the work in 1767, which is 1 year after he returned to Russia after his stint in Berlin. So that's going to take us over to Joseph Louis Lagrange. He was born a little bit later. He was born in 1736. He is Italian, despite the evidently French name, and that's in part because of his later time at the French Academy of Sciences. But as an Italian, he was working in Torino, the Turin Academy of Sciences, and he was making a really big name for himself. And so I also want to make sure that I go back to correct my headcanon a little bit and note that it's not like this was a pity award to name these things after him. He was a pretty good mathematician in his own right, especially knowing, as I did a little bit more reading, that Euler actually tried to get Lagrange to come to Berlin as early as 1756, when he was only 20. He was getting these emails from Euler saying, hey, you really need to come to Berlin and work with us because this is a great place to work. And well, Lagrange didn't until Euler was ready to leave. Maybe Euler was, a little bit too intimidating to work with as a coworker. So anyway, in 1766, Euler returns to Russia. Lagrange takes over his position at the Royal Prussian Academy of Sciences in Berlin. And so there's this little bit of an overlap where it seems that Euler already had this idea, was already working on these nice balancing points that exist in gravitational dynamics. And so he publishes the first 3, and then a few years later in 1772, Lagrange comes along and he publishes the existence of these 2 other points that Euler himself wasn't even aware of. And so eventually, well, Lagrange makes his way to France at a very inopportune time in history to make his way to France. And well, that's the end of this little bit of a history lesson, aside from going through one more slide to show you a picture of Lagrange and all of his varying names, both the French stylized version and the Italian stylized version, and also one of his papers on the problem of 3 bodies, the 3-body problem. Okay, so that's going to take us back to these Lagrange points. So all of the examples that I've been talking about so far have been talking about the sun and the earth, but I also want to make sure that it's really clear that these points exist for every pair of solar system bodies that are in orbit around each other. And so there are these 5 balancing points for the earth and the sun. There are these 5 balancing points for the Earth and the Moon. There are these 5 balancing points for the Sun and Jupiter, for the Sun and Neptune, for Saturn and Titan. Any pair of massive bodies in orbit around each other have these nice balanced points. And so let's talk about the math. And well, I'm not going to go too much detail into the math. There are some great explainer videos on YouTube that talk you through how to solve these. There's one that I'm going to show a screenshot of in a couple more slides that is very intimidating looking, but there are some others that talk you through it in a little bit more detail. But those videos are, on the order of 50 minutes long, and, talking about math for 50 minutes is a great way to get me thrown off this show. So let's talk just about a little bit about some of the math. So there are two different sets of forces that we're trying to balance here. There are the gravitational forces, and there are, well, also the momentum, the actual velocity changing as this thing is moving its way around the sun, which in part is still, governed by the gravitational forces. And so let's just think about this for a couple of seconds. So we've got our sun all the way up here at the top, and we've got our eight planets going down our column. And each one of these planets gets a little bit further away from the sun. As it gets a little bit further away from the sun's gravitational influence gets a little bit weaker. As a result of that, the required velocity necessary to stay in orbit around the sun drops and drops and drops as you move further out into the solar system. And that's what gives each of our planets, in part, a different orbital period. We've got Mercury that's racing its way around the sun every 88 days. We've got the Earth that takes exactly 1 year, what a coincidence, to make its way around the sun, all the way out to Neptune, which takes 165 years. And so we're saying that there's this L1 spot right here that is a little bit closer to the sun than the Earth is. And there's this little spot here, L2, on the other side of the Earth, a little bit further from the sun than the Earth is. And so if the only thing that we needed to worry about was this distance, then we would make the assumption that, well, our orbital velocity at L1 is going to be a little bit faster than what we have for Earth. And our orbital velocity for L2 is going to be a little bit lower than what we have for Earth. And so the orbital period for something at L1, just thinking about it in terms of orbits, should be a little bit less than a year, and for L2 should be a little bit more than a year. But then we also have to think about the gravitational aspect. And here, maybe a good intuitive way of sort of thinking about it is just thinking about the gravity of the Earth. So we've got something here in orbit around the sun at L1, and it's trying to make its way along its orbit a little bit faster than Earth's orbit. It's trying to make its way, around the sun in 360 days instead of 365 days. As it keeps trying to move its way forward, Earth's gravity is pulling it back. Earth's gravity is tugging it back into this L1 point. And the same thing kind of goes for L2. So in L2, maybe it's something like 370 days would be the optimal orbital period for something at this location. And so it's slowly trying to drift its way backward, taking a little bit less time to orbit, or a little bit more time to orbit the sun than the Earth does, orbiting the sun a little bit slower than the Earth does. But as it keeps drifting back, the Earth's gravity is going to keep pulling it forward and trying to maintain it in this location. That's something that we actually see in a variety of different places in the solar system. And one of them is in the rings of Saturn. So the rings of Saturn have these shepherd moons. And I guess the rings of all of the gas giant planets occasionally have some of these shepherd moons. But this is Saturn's F ring, and it's gravitationally bound by these two moons, Prometheus and Pandora. And you can see some of these gravitational influences in the individual ring particles as they're being contained inside of this really narrow orbit. And so Pandora is working to slow these things down. Prometheus is working to speed these things up. And they just kind of get gravitationally trapped in this nice little narrow band. So it's not a unique thing to our Lagrange points. This is orbital dynamics. This is something that happens whenever we're trying to balance orbits with gravity. Okay, so we need to start thinking about this in terms of forces then at this point. What we've got here, not to scale, is the sun over here on the left, and we've got the Earth over here on the right. And in the middle, hopefully it's coming through well enough, we've got this tiny little spacecraft. And maybe it'll be a little bit more visible when I start adding in some of the labels. And so let's start thinking about some of the terms that we need for these gravitational formulations. So Newton's gravitational laws require some mass and some distance. And mass is pretty easy because mass is just something that's inherent to each of these bodies. And so let's say that the sun, well, it's big and important. It can be number 1, so it gets mass m1. And the Earth gets the mass m2, and our tiny little spacecraft, which has to be a lot smaller than the Earth and the sun, gets a mass of m3. And then we need to start thinking about some distances. And I guess I probably should make clear that this is L1 that we're looking through in this example, again, because L1 is maybe the more intuitive of the 5. And so here's our spacecraft at L1 in between the Earth and the sun. So distances. Well, we know that we're going to have the distance from the sun to the Earth. That's something that's pretty well known at this point. And so we've got the capital R that can represent the distance from the Earth to the sun. And then we know that there's going to be some distance between the center of the Earth and where we want to put the spacecraft to get this nice gravitational and orbital balance. And this is what we're solving for. We're trying to figure out what this distance is. How far do we need to park this spacecraft away from Earth so that it stays there, so that all of these points are balanced and all of these forces are balanced. And so here's our force of the Earth interacting with the spacecraft. We've got Newton's gravitational constant. We've got the 2 masses, and we've got the distance between the 2. And we've also got the force of the sun interacting with the spacecraft. And so again, gravitational constant, m1, m3. And now the distance between the sun and the spacecraft is the distance between the Earth and the spacecraft minus the distance between, or the distance between the sun and the Earth minus the distance between the sun or the Earth and the spacecraft. Too many things to talk through. So here's what our math looks like. The equations are a little bit easier to talk through than saying sun and Earth and satellite 20 times, evidently. But then also remember that there's this orbital component. And so there's this angular momentum that the spacecraft is going to have as it keeps trying to work its way around the sun and trying to pull its way forward ahead of the Earth. So we're trying to balance out all of these forces. We're trying to solve this lowercase r. And so then a bunch of fancy math happens. I like this comic, then a miracle occurs in the middle of this proof. I'll put up a screenshot of the math in a couple of seconds. But what the solution eventually works out to is this. So our value for this lowercase r, our value for this distance between the Earth and the spacecraft that is optimal for this gravitational balance is tuned to distance between the sun and the Earth. So the distance between the 2 gravitational bodies is important. And then we've got a cube root with a relationship of the mass of the Earth, m2, and 3 times the mass of the sun, m1. What this works out to is the distance that you saw before for L2. It's about 1.5 million kilometers. It's about 900 and some thousand miles. That's how far we have to get away from the Earth in the direction of the sun to get this nice balance. And if you're familiar with some of the other equations of physics, this turns out to be the same equation that we use for the Hill sphere, where the Hill sphere is the region of space where the Earth's gravity or the gravity of any planet has more influence over things in that area than the sun's gravitational field does, which makes sense because we're looking for the balance point between the gravitational field of the sun and the gravitational field of the Earth. It's natural that that balance point would be right at the edge of the Earth's overwhelming Hill sphere influence. So this is a solution for L1, and if we want to get really, really terminology specific about it, this is one of the 5 equilibrium solutions to the differential equations of motion for the circular restricted 3-body problem. That's a mouthful. Here's what that mouthful looks like in overall math form. And again, as I mentioned, there are several videos on YouTube that talk you through all of this math in a lot of detail. This one's using some slightly different notation than I was just using. So they've got this capital L, which represents the same thing as the lowercase r that we were trying to solve for. They've got this lowercase r sub es, which is representing the capital R, the distance between the Earth and the sun. But what it eventually works its way down to is the same thing that we just saw in that equation that I had put up. That whole big messy thing about the circular restricted 3-body problem, there's our solution. So that's L1, and remember that we've got 4 other Lagrange points that we need to think through. So where are these other Lagrange points going to be? Well, we're going to have some gravitational balance on the other side of the Earth as well. And so we just flip around some of the signs. Now the distance between the sun and the spacecraft is going to be the distance between the sun and the Earth, and then the Earth to the spacecraft. And so we have some R plus R's instead of R minus R's. But what it eventually works out to is the same exact formula, which again makes sense because, well, we called it a Hill sphere, this sphere of gravitational influence. Spheres are nice and round, right? They should be about the same size going from the center out toward L1 as they are from the center out toward L2. And so the math eventually coincidentally works out that the distance to L2 is basically the same as the distance to L1. All right, L3. So L3, if you'll recall, is the one all the way over on the other side of the sun. And as I was preparing this talk, for the longest time, I was thinking it is the exact opposite point from the Earth. It is, on the Earth's orbit, just on the opposite side of the sun. Turns out that's not quite so true. And there are a variety of depictions that are a little bit inaccurate at showing where L3 is. Let's look at a couple of them. Here's the first one I put up. And here's L3. You can see the point is definitely drawn right on the Earth's orbit. If you want to get, pixel perfect, maybe it's a little bit further out than Earth's orbit. The center of the point is a little bit to the left of the orbit, but, the point is drawn on Earth's orbit. And so it's trying to communicate that it's basically there. Here's the nice topographic map of the gravitational fields. And here our point definitely is on the outside of the Earth's blue orbital ring. It's just a little bit outside, but they show it definitely on the outside. Here's the nice 3D rendering, and here our point is, again, definitely on the outside. It's on the outside of this nice green ring that's trying to signify the Earth's orbit. But here was the easy on the eyes version, and this time L3 is well inside this ring that represents the Earth's orbit, or in this case, just generally the orbit of this second mass, M2. And so which of these is correct? Is it right on the Earth's orbit? Well, I already kind of hinted that that's not the case. Or is it a little bit outside? Is it a little bit inside? Is it a lot outside? Is it a lot inside? Turns out that it's just a little bit inside. And if you go through and you work out all the math, you get this very slightly different looking equation. It still relies on all the same terms. We're still solving for a lowercase r. In this case, our lowercase r is the distance inside of the Earth's orbit. So we've got this longer 2r, which represents 2 times the distance between the Earth and the sun, because Earth, sun, and then all the way over to Earth on the other side. But then we have to come back a little bit because, well, both things are pulling the spacecraft to the left. The Earth is pulling the spacecraft to the left. The sun is pulling the spacecraft to the left. And what it eventually works its way down to is this, again, relationship between the distance between the Earth and the sun and the masses of the Earth and the sun with some other constant thrown in. Turns out that this works out to about 163 miles. So L3 is 163 miles inside of Earth's orbit on the other side of the sun. So those were Euler's contributions to this presentation. Now let's actually get to the Lagrange contribution to this presentation. L4 and L5. Well, these are both, it turns out, equilateral triangles. And so we've got this distance r between the Earth and the sun. That's going to be the same distance r between the sun and our spacecraft. And because it's an equilateral triangle, that's also going to be the distance lowercase r between the Earth and the spacecraft. So we've got these 2 different points that are 60 degrees ahead of the Earth and 60 degrees behind the Earth, where we've got this bigger, broader, gravitationally stable region. But these regions come with some caveats. And one of those caveats is about the mass relationship between our 3 bodies. But it turns out that if the mass of the Earth was more than the mass of the sun divided by 25, which is definitely not the case, then we would end up with no L4 and L5 that are valid. The mass relationship doesn't work out and these become gravitationally unstable points. The same thing goes for this relationship between the mass of the Earth and the mass of our spacecraft. If we ended up launching a spacecraft that has a mass that is about 3 times the mass of the moon, we can't put it at L4 because that's going to be a gravitationally unstable point at that point. And this actually does come into play in our solar system because the mass relationship between Pluto and its moon Charon is less than that 25-1. And so our Pluto-Charon system, well, it's got its L1 and it's got its L2 and it's got its L3. But because the mass of Pluto is only 8 times greater than the mass of Charon, well, we fail this constraint, and so we don't have L4 and L5 points that are gravitationally stable in this system. All right. Hopefully you're all still awake. You made it through the math. You made it through the forces. Let's get back to talking about L2, and let's get back to talking about the James Webb Space Telescope. So we've got this model set up now. We've got the sun sitting here nicely in the middle of the solar system. We've got the Earth, not to scale, a little bit further off to the right. We've got the James Webb Telescope sitting all the way out here at L2, again, not to scale. We're good. We just need to put the Space Telescope there, and it's going to stay there. Turns out that it's a little bit more complicated than that. So let's go back to that big mouthful that I mentioned before, the equilibrium solution to the differential equations of motion for the circular restricted 3-body problem. There's 2 big problems with that. There's the circular part, and there's the 3-body problem part. So let's start with the circular part. The circular part automatically fails right from the very beginning because the Earth's orbit is not a circle. The Earth's orbit is elliptical. And because the Earth's orbit is elliptical, there are some points in the orbit when the Earth is closer to the sun. There are some times when the Earth is further away from the sun. That means that inside of our nice balanced forces, that capital R is going to change. And because the lowercase r, that distance to L2, is dependent on capital R, that means that our location of L2 is going to change. And so every single second, the Earth is moving its way around the sun. It's changing its distance to the sun slightly. And so the location of L2, that mathematically balanced point for L2, is going to change essentially every single second. The second problem that we need to start thinking about is the 3-body problem. So if the entire universe was only made up of the sun and the Earth and the James Webb Space Telescope, then, well, at least we would pass that problem. But there are complications. And the first complication is that big annoying bright thing in the sky that we all hate unless we're doing the lunar observing programs. It's about an 81st of the mass of the Earth. And so, 1.2% the mass of the Earth, but that's still a pretty big number. And so it still has a pretty big gravitational influence. And sometimes it's on the same side of the Earth as L2. And so anything that exists at L2 is going to be pulled a little bit more toward the moon in this case. But then sometimes, well, the moon is over on the other side of the Earth. It's still pulling in the same direction, but it's not pulling as strongly because it is further away. And sometimes the moon is over here, which means that it's still pulling a little bit to the left, but it's also pulling a little bit forward in orbit. And so we've got this extra messy thing with the moon changing the gravitational balance. We no longer have a 3-body problem, we have a 4-body problem, and that breaks all of the solutions that we talked about with respect to these Lagrange points. And it's not just the moon. We've got other big things in the solar system as well. We've got this big planet called Jupiter, which has a huge amount of gravitational influence, even though it gets no closer than about 400 million miles away. And it can sometimes be pulling on the James Webb Space Telescope or anything else that we want to put at L2 in the other direction. Unless, of course, it's at a point in its orbit where Jupiter is over here, in which case it's going to be pulling on the James Webb Space Telescope or anything else at L2 in the other direction. And we've got other big planets as well that aren't going to have as much gravitational influence, but still can screw things up inside of our orbital dynamics. And we've got this other planet, Venus, which is about the same size as the Earth. It's going to be still pretty distant. It doesn't get much closer than 25, 26 million miles. But at the same time, sometimes it's pulling from a distance of 26 million miles, and sometimes it's pulling from a distance of 160 million miles. And so all of these are going to be changing this nice gravitational balance, solar system wide. And so 2 conclusions that we can draw from this immediately is, well, again, the exact position of L2 is going to be constantly changing because this distance between the Earth and the sun is going to be constantly changing. And even if we put the James Webb Space Telescope right at L2, that's not even the point of solar system scale gravitational stability. And so we're going to have a problem if we just put it at L2 and expect that it's going to stay at L2. But let's say that we did. Let's say that we put it exactly at L2. How long is it going to stay there? Let's go back to our nice little plot of all of these different Lagrange points, which we've now broken. These points are obviously still going to be useful, because why else would we put a $10 billion space telescope at L2? Well, it turns out that L1 and L2, if you put something there and you just left it alone, it's going to stay at that point for, on the order of 23 days. That's the number that I seem to read the most often. And so 23 days, it's going to start drifting to the point where, you have to start firing some thrusters to be able to correct for it. That's not great. And so we're going to have some problems if we just stick it right at L2. We're going to have to come up with some other solutions. If you're curious about some of these others, the number that I saw most often for L3 is about 150 years. Something's going to be stable there for L3 for about 150 years, and then it's going to start drifting a little bit too far. L4 and L5, well, those are a little bit harder to define. And so I'm just going to give the very, very scientifically rigorous a while. And this is because, well, again, these aren't, well, they still are points, but the gravitational forces end up making them regions. And a good example of this is to look at the Trojan asteroids that are co-orbital with the planet Jupiter. Here's a nice little NASA animation. All of these green points are the location of these different Trojan asteroids before Jupiter in its orbit and beyond Jupiter in its orbit. You can see if you watch this animation carefully with respect to where I'm putting this dot, Jupiter is moving closer and further from the sun because its orbit is also elliptical. This is kind of trying to keep this line between the sun and Jupiter even in place. And you can see that all of these things are still nicely captured inside of L4, still nicely captured inside of L5, but they're moving around. And because these things are so small in relation to the mass of the sun, in relation to the mass of Jupiter, they can stay there for a reasonably long period of time. But if we end up breaking that mass relationship, if we try to put something more massive at L4 or L5, we can have some problems. And those problems occasionally, at least as far as scientific theories go, end up with the creation of that annoying bright moon up in the sky. So one of the most highly regarded theories behind the formation of the moon is that, well, there was this other planet, Theia, and this other planet, Theia, well, it might have stayed gravitationally balanced along with the Earth's orbit at L4 or L5 for a while, but a while is a pretty short amount of time with respect to the overall time scales of the solar system. And so eventually it got to the point where it was a little bit less stable in its orbit, and it was probably, a little bit closer to the mass of the Earth than something tiny. And so it probably failed that 1:25 relationship. Eventually they slammed together, and well, after everything settled down, we had a new moon. And we had a slightly larger Earth as well. Again, probably failing this relationship. Okay, so James Webb Space Telescope, we got to come back around to that. The James Webb Space Telescope, as you saw in some of the animations earlier, it looks a little bit like this. It's got this big sun shield down here at the bottom, and the goal of the sun shield is to shield the instrument from the sun. And this is because, well, as an infrared observatory, it needs to keep its instruments cold, and it needs to keep all of these other heat influences away from interfering with its imaging. And so here's something that I got from the James Webb Space Telescope website a couple of months ago, showing the temperatures on the sun shield side being fairly comfortably warm, maybe a little bit too warm unless you like living in Death Valley. But over here on the cold side, we're talking close to -375, -380 degrees Fahrenheit, cold in Celsius, cold in Kelvin as well. And this is going to be really important with respect to trying to put this telescope somewhere close to L2. And here's why. Again, let's say that we put this telescope over here at L2, and our telescope has a hot side facing the sun, and it has a cold side facing away from the sun. But Jupiter ends up being over here. And so Jupiter is going to start tugging on our James Webb Space Telescope craft, and it's going to start pulling it away and away and away from L2. And again, once it gets so far away from L2 that it just kind of generally leaves the region, we're going to lose the telescope. Unless we turn the telescope around and start firing its thrusters to get it back over to L2. That puts the imaging side of the telescope on the hot side of the telescope. And as my little emoticon shows, that makes astronomers sad. So we don't want to do that. And so the solution actually turns out to be that the James Webb Space Telescope is positioned a little bit closer to the Earth than L2. And the idea here is basically, well, if here is our sun, here is our Earth, and here is our L2 point, if we put the Space Telescope on the Earth side of L2, over time, the Earth's gravity is going to win this battle. It's going to start falling down the gravity well in the direction of Earth. We can fire the thrusters and we can start pushing it back towards L2 a little bit. And as long as we don't fire that thruster for too long, we can start pushing it back toward L2 and we can wait for gravity to start drifting it back a little bit. And that works out really nicely for us because then we can keep the cold side of the telescope away from the sun and we can keep doing science. There's another reason why we probably don't want to put a telescope exactly at L2, and that's the fact that a lot of our spacecraft are still solar powered. And if we put it right on the other side of the Earth from the sun, well, it's not going to get quite as much solar power. It turns out that L2 is a little bit outside of the Earth's umbra, so this is still going to be a penumbral eclipse, but it's going to be enough to really cut down on the amount of power that we can get to the space telescope. So we don't want to put something exactly at L2 because, well, then it's not going to get any sunlight, or it's not going to get much sunlight. So the final solution ends up being a really nice pair of orbits that are called halo orbits and Lagrange orbits, assuming that I'm pronouncing that second one correctly. And what basically ends up happening is we can design orbits that orbit around L2. Even though there's nothing at L2, even though L2 is just this gravitational location in space where there's no mass, we can design something where the forces balance out just nicely enough so that James Webb and any other mission that we put at L2 can stay there for the long term by just generally orbiting around this location. And if you want another view of what those look like, because they were a little bit abstract in the visualization sense, imagine an orbit that looks kind of like this, where it's drifting to the left, it's drifting to the right, it's drifting forward, it's drifting backward a little bit. There's a really great YouTube video with a visualization produced by NASA that shows this orbit in 3D, but I was never able to actually get it embedded successfully in PowerPoint. So that's really the bulk of the presentation as far as James Webb goes, but I want to talk a little bit about some of the other uses of the Lagrange points before I really step away and take a couple of questions. The first thing to talk about is the fact that, well, L1 and L2 are really popular as far as space missions go, which makes sense because we can put spacecraft away from the Earth in a reasonably gravitationally stable place and let them stay there for long periods of time. And so here's just a quick summary of the space missions that are currently at L1 and currently at L2. We've got SOHO, which is off observing the sun. We've got Discover, which occasionally takes really nice full Earth images in photos. We've got Gaia that's doing a lot of photometrics and trying to determine distances to stars sitting out at L2. We've got James Webb sitting out at L2, but this is just active missions. We can also think about some past missions. And so there are a variety of missions that either for part of their mission or for the entire mission were sitting out at L1 or L2. And then we've got planned missions, which are not quite as easy to find images of because they're planned missions. And so I had to use a little bit of a futuristic spacecraft design to show these missions. We've got lots and lots of things that are planned for L1 and L2 missions coming up in the future. What else might we find at these Lagrange points? Well, the first thing that we can start thinking of is asteroids, because these L4 and L5 points are really, really convenient with respect to keeping things and trapping things that are of low mass with respect to the other two masses. Jupiter, far and away, is the planet that has the most of these captured asteroids at their Lagrange points. But we have a couple that we found for other planets as well. We found an asteroid at the Sun Venus L4. We found a couple of asteroids at the Earth Sun L4. We found a bunch of them all the way out at Neptune. Earth Trojans, it turns out, despite the fact that they're nice and close to us because they're at our L4 and L5 points, well, they're tough to find both because of the small size and because of the proximity to the sun. We can only see them a little bit before sunrise, a little bit after sunset, and then they start to drop down into the atmosphere and we start to have problems locating them. The big surprise that I came up with here is that we don't know of any Saturn Trojan asteroids. And so I went off and I tried to do a little bit of research, and I found this paper called "Where Are the Saturn Trojans?" And it turns out that when they did some of their mathematical modeling, what they found is that the the Sun, Saturn, L4 and L5 points turn out to be really gravitationally influenced by Jupiter, because Saturn's orbit is so large and L4 and L5 are so far away from Saturn, and because Jupiter is so massive, well, Jupiter starts tugging things out of those L4 and L5 semi-stable positions. So, too bad for Saturn, but it turns out that Saturn also has some other interesting Lagrange relationships. So here is Saturn and two of its moons that you can go out and see with a reasonably sized telescope, Tethys and Dione. And it turns out that both of these moons have co-orbital moons at their L4 and L5 points. And so we've got Telesto, which is orbiting a little bit ahead of Tethys, 60 degrees ahead of Tethys. And we've got Calypso that's 60 degrees behind Tethys, and they're co-orbital. The same thing for Helene and Polydeuces with the other moon, with Dione. And so the fact that Saturn doesn't have any Trojan asteroids, well, let's not be too sad about it, because these are the only instances that I'm aware of in the solar system that we've discovered co-orbital moons orbiting planets. And to have two pairs of them is really incredible. What about the Earth and the Moon system? We said that any two massive pairs of bodies that are in orbit around each other have these Lagrange points. And it turns out that there are things that are kind of similar to the zodiacal light called Kordylewski clouds that exist at the Earth, Moon, L4 and L5 positions. Basically, think of it as a bunch of trapped dust that exists 60 degrees ahead of the moon's orbit and 60 degrees behind the moon's orbit. They get a little bit tricky to see because, well, they can be blended in with some of the zodiacal light, and, well, the moon is going to be pretty bright anytime you can see them above or below the horizon. And so this is something that was only recently confirmed as a discovery only a couple of years ago, even though it was mathematically suspected since, I think, sometime around the 60s. Other potential uses for these Lagrange points coming up in the future, aside from some of those other space missions that we've talked about. So Arthur C. Clarke, the sci-fi author, one of the things that he had proposed in some of his other works was this idea of putting spacecraft at geostationary orbit. But it turns out that he also came up with this idea of putting some futuristic spacecraft at L2, or at least orbiting around L2 of the Earth-Moon system, where the logic is we've got something orbiting around Earth-Moon L2. That means that we can send signals off to this satellite sitting all the way out there, and then that satellite can reflect those signals, can bounce those signals to potential space missions on the far side of the moon. Well, that actually has become a reality because China landed a lander on the far side of the moon, and they have a relay satellite which is orbiting around, or was orbiting around, L2 and maintaining communication between this lander, which is otherwise not able at all to contact Earth, and the Earth command centers.
Interesting.
A couple more. So the B612 Foundation. The idea behind this foundation is that they really want to try to find potential Earth impactor asteroids that are coming from the direction of the sun. Well, that's pretty difficult because the sun is big and bright. And so if something is coming from that direction toward Earth, we're going to have a hard time seeing it. So what they've proposed is to put a Sentinel satellite at the Sun Venus L3 point so that it can look away from the sun. It can look outward toward the distant reaches of the solar system and look for something that could be potentially on a collision course with Earth. Of course, if this is going to be on the opposite side of the sun from Venus, it's also going to be on the opposite side of the sun from Earth. And so we're going to need another one of those relay satellites, maybe off at L4 or off at L5, which can bounce signals back and handle the necessary communication. A satellite at the Earth-Sun L3 can really do some good things for helping us monitor solar storms on the other side of the sun. And this is especially true with solar maximum coming up, as we saw in the earlier presentation. So if there's going to be an active region on the other side of the sun, it would be pretty great if we had the ability to have a satellite on the other side of the sun, which is something that the stereo spacecraft were doing for a while, but they weren't actually positioned at L3. They were just in orbits that were drifting the spacecraft toward the other side of the sun over time. Again, this is going to be something that requires us to have another communication satellite to be able to talk to Earth from the other side of the sun. But there's another benefit to potentially putting a satellite at the Earth-Sun L3, and that is enabling communication with Mars whenever Mars is on the other side of the sun from Earth. So right now, we lose contact with our rovers, we lose contact with our orbiters around Mars for about a week or two every year during solar conjunction. Well, if we had a spacecraft that was on the other side of the sun all the time, whenever Mars drifts over there, we can still communicate through several bounces now this time with all of our missions to Mars. Another interesting idea, and now we're starting to get really far out there, really starting to dream big. So the whole idea of terraforming Mars gets a little bit difficult because Mars is too small to really retain a good atmosphere. And it also doesn't have a magnetic field that would also help to keep that atmosphere in with the solar wind constantly blasting Mars. So what's a really out there solution? Let's take a giant magnet and let's put a giant magnet at Sun Mars L1. And this giant magnet can create a big enough magnetic field to start to prevent the new terraformed atmosphere of Mars from being pushed away. And so that would enable a little bit better with future space missions, with future terraforming, future colonization. There's also this L5 Society, and the L5 Society was founded to promote some of these space colony ideas that Gerard O'Neill created. And so L5, well, it's named after L5. It's a proposed location along with L4 for putting something like a huge rotating space habitat. This is what's called a Stanford torus. And so the idea would be you've got this big rotating ring and people can live on the inside of the ring. The ring spins to give us a nice gravity simulation. And because it's nice and balanced at the Earth, Moon, L4 and L5 points, well, we can put things there and let them stay there for long periods of time without needing any extra corrections, without needing any extra gravitational influence. The very last thing that I'll mention is this whole idea of the interplanetary transport network. And the idea here is that we can make use of these Lagrange points to efficiently move through the solar system with very, very little energy used. Imagine putting a spacecraft at the Sun-Earth L2 and then just giving it a little kick. And this little kick needs to be timed perfectly, but if you time it perfectly, this spacecraft can then just start drifting through space and eventually get trapped at, say, the Sun-Mars L2 or the Sun-Mars L1. And then it can start going through any other course corrections that it needs to. And, well, you end up with a very cheap propulsion method, but also a very long propulsion method to get a probe out to some other point in the solar system. And some of these ideas have been tested. The Genesis Solar Wind Sample Return mission actually used some of these ideas, trying to come up with an efficient way of transitioning that spacecraft to where it needs to be for its mission. So I've definitely talked longer than I promised, but, well, we got to take advantage a little bit of the fact that the early program went a little bit short. And so I guess at this point, I'm happy to take any questions that anybody has.
Okay.
Yeah, I have a comment to make, John.
Sure.
If we are going to understand the James Webb Space Telescope, it is imperative that we understand at the beginning the Lagrangian points and their history and their use. And John gave us a full description and discussion of this, which is really fundamental to our understanding of what we hope to get out of the Webb telescope. I first heard of the Lagrangian points when I began working with Gene Shoemaker and Carolyn Shoemaker. They were about to begin a study of the Lagrangian L4 and L5 asteroids near those points of Jupiter. But in the early summer of 1990, while Gene and Carolyn were in Australia, I photographed and discovered an asteroid that turned out to be the first one at the Lagrangian 5 point of Mars's orbit. We decided to name that one Eureka, which has since been transformed into the name of my telescope that Scotty has provided me with. And that's one of the reasons why it is such a very special telescope named for an extremely special asteroid. And today, we thank you for a very extremely special presentation. Thank you, John.
Thank you. I really appreciate that comment. Yeah, thanks.
Other comments was Jeff Wise watching on YouTube says that was outstanding. Joe Schmuckatelli says, John, you crushed it. Thank you so much. Norm Hughes says that was an amazing presentation on the complexity of the Lagrange points.
Thanks. I definitely appreciate all of those comments. I'm still trying to adapt to the ability to accept so much praise, but I do appreciate them all. Thank you.
Well, you walked them through it, and so that was fantastic.
Yeah, I definitely learned a lot more than I actually knew, which was not much. Thank you. That was an excellent presentation.
Yeah, and I learned a lot putting it together as well. It was a pleasure to be able to present it for a second time.
Well, we're glad you did. Thank you so much. Does anybody else here have any questions?
Presentation. I knew enough to be dangerous about the whole discussion, and that really brought it in more understandable type usage.
Thank you. All right. Well, thank you. And John, again, thank you. I learned a lot. It's kind of overwhelming because I never really thought about it. Yeah, there's a lot to comprehend here.
But you start to get some ideas. So new possibilities of space travel and communication, so it's very cool.
It is. It's amazing when you really stop and think about it. It's really amazing. I actually thought that if something set at L1 or L2, it would stay in that orbit. I did not really think about the drift and the pole, so that's amazing.
Yeah, when I was first putting this presentation together for the Roanoke group, I was thinking at the beginning, how am I going to talk for more than 15 minutes about Lagrange points? And well, you just heard me ramble for an hour like I do to my classes. So there's a lot there that I probably could have included that I didn't.
Yeah. Well, thank you. Thank you so much. We really do appreciate that. So, all right, I am going to go over, I'm going to share my screen and go over the answers to the questions. And thank you everyone for the answers. There we go. All right, how wide is the cosmic bubble that surrounds Earth? It is 1,000 light years wide.
Oh.
Michael Overacker got that. How many seconds has the Hubble Space Telescope been operating since January 1st, 2022? 1 billion seconds. That's amazing. And Josh Kovac will be receiving a calendar. What astronomer coined the name Aurora Borealis? Well, that was Galileo Galilei in 1619, and Barbara Brown got that one. So she will be receiving a calendar. So thank you again, everybody, for your answers. We really appreciate it. And someone from the Astronomical League will be in touch with you before long. So tonight, I'd like to thank Scott Roberts, our broadcasting genius. I keep that up there. And David Levy. We always appreciate all of the readings from David. They are amazing. Thank you, David. And Carroll Iorg, Astronomical League president, thank you for being here and showing us and telling us what's coming up in the league. And John Wenskovitch, thank you. That was an amazing presentation. That really gets you thinking. All right, and join us again for Friday, May 13th at 7 p.m. Eastern Daylight Time. We will have Dr. Jessica Novello. She will be speaking on the cryovolcanism in the solar system, the coolest geological process. So we will have Dr. Jessica Novello with us. So please join us on Friday, May 13th at 7 p.m.
Very
And
cool.
yeah, it'll be exciting. We have had some excellent speakers tonight included. Really
Yes.
enjoy. We've learned so many different things about everything. You know, I think that's what I really like about being on Zoom is you can reach out so much further, and everybody specializes in so many different areas, and we get the benefit of being able to invite them along. So thank you, John, again, I appreciate it. And thank you, Carol, David, and Scott. You guys are amazing. Thank you for putting up with this every month.
Thank you. There was a question towards the end. People were wondering if they could get a copy of your presentation, John. You know, where can people find out more information from you?
Yeah, I'm definitely happy to share the slides. From my experience sharing them earlier when some of the Roanoke folks asked, they're a bit too big to attach to an email. But I'm definitely happy to put up something like a Google Drive link. And so you can definitely reach out to me. The easiest way is maybe just going with my full name, John Wenskovitch @gmail.com. Or you can definitely contact me through the rest of the folks who are here on the call. And I'm happy to share them. I guess the other possible constraint, well, constraint probably isn't the best word, but you saw the presentation. The presentations were very image-based, and then you got my voiceover. If you're just going to stare at the slide, you lose that voiceover, but hopefully you retain enough to get the general idea.
Well, the other way is you can rewatch this program on the Astronomical League's Facebook page where it's permanently recorded. So that would be an easy solution as well. So because without the voiceover, well, you explain so much. So
Yeah, definitely. Okay. Anybody got anything else?
I think that's it.
All right. Well, thank you again to everybody on the program, and thank you to everybody that's watching. We really appreciate it, and we will be back on May 13th. Please join us then.
Thank you.
Thank
Not
you.
everybody.
Scott. Yeah, do something with that cowboy.
Yes, everybody
hat.
would like to say goodbye.
Thanks, Scott.
The new look there.
Yes.
All right.
Yeah. All right. Thank you, everyone.
Thanks,
And
everybody. And
thanks,
we will
everybody
see you
watching.
on Monday with more programming. So thanks for watching and take care. And thank you to the Astronomical League. Take care.
Thank you, Scott.
Thank you.
Bye-bye.
Bye-bye.